Hello, Integrated Math 1. Welcome to lesson 1.1.3a. So this is day 1 of this lesson. We're going to take a couple days over this one because it's got a lot of stuff and it's kind of really important. So we're going to really take our time. We're going to take a few days to go through this. Before we jump into today's lesson, though, we do want to do a quick little warm-up just to kind of get your brain going. We're asking you to identify the domain and range of the relation described by each set of ordered pairs. We're also asking you to write an equation using the variables x and y that could map the domain to the range. Now, this is going to sound wordy, so let me point out a few things. First of all, we're on page M1-39 of your workbook. If you're not sure where we went, that's where we went. That's where we are. The other thing is you might be a little confused by domain and range. Don't be. You've heard these terms before, and they're going to come back at us pretty hard and strong from now on. They're just going to be coming at you every math class you ever take now. It's just how it's going to be. So when we're talking about the domain, we're talking about our independent variable, also known as x, right? What are our x variables? What are our x coordinates, our x possibilities? When we're talking about the range, we're talking about y. We're talking about our dependent possibilities. So with that in mind, go ahead and list off, looking at these guys, we got a pair. List off for me the domain, list off for me the range, and then see if you can write an equation that shows the pattern, that shows the relationship. They say map the domain onto the range, but I say show the relationship, same stuff. Go ahead and hit pause to work this out and then hit play to check your work. So first of all, the domain we said was x. So -3 is the x coordinate, -2 is the x coordinate, -1, 0, and 1. Those are all my x coordinates. So that's my domain. My domain is -3, -2, -1, 0, and 1. Which means that my range is all the y coordinates. So -6, -4, -2, 0, and 2. Boom, there's my range. Now, let's write an equation. Let's look for a pattern. How does my -3 become a -6? How does the -2 become a -4? How does a -1 become a -2? 0, 0. And how does 1 become a 2? I don't know if you've noticed it or not, but if you multiply each of those items in your domain by 2, if you double it, you multiply it by 2, you get every item in your range. So we have to multiply our x coordinates by 2 to get y. So I wrote y equals 2x because if you double the x coordinate, it equals your y coordinate. And that's all there was to it. It really wasn't that bad. It felt bad. It wasn't bad. So today's lesson, we're going to be recognizing functions and function families. And like I said, we're going to be doing this for a couple of days because there's just a lot to cover. It's not hard. There's just a lot to cover, and I want to make sure that we really get it all. So today's learning goals, we're going to define a function as a relation that assigns each element of the domain to exactly one element of the range. We're going to write equations using function notation. We're going to recognize multiple representations of functions. So there are more goals that we'll do in the coming days, but these are our goals for today. Now, if you're looking at page M139, there are so many key terms. We're only going to cover some of those today, like relation, domain, range, function notation, vertical line test. I believe we're also covering, sorry they're not up here, I believe we're also covering discrete and continuous relations as well. That's also going to come up. So sorry those aren't on my screen. Those are coming. So you've sorted graphs by their graphical behaviors, right? We were playing with our graphs and we were kind of sorting and we were playing with them a little bit. We're going to be playing with those graphs a little bit more today and in the coming days. So how can you describe the common characteristics of the graphs as functions? They have things in common. So what kind of functions are they? Does that make them belong to a particular family? We're going to be finding that out. So let's go to our getting started activity on the next page, M1-40. And you have a whole bunch of graphs here. You have 4 different graphs. There's no right or wrong answer. All I want you to do is decide Which of these graphs shown does not belong with the others? And just give me a reason why you've decided one of these graphs is not like the others. There's no right or wrong here. I'm just curious what you're doing. So make some notes. Which graph is the weird one? One of these things is not like the other, and why? Go ahead and hit pause to jot down your thoughts and then hit play when you're ready to check your work. So you may have picked any one of these and may have had all kinds of reasons. For me personally, I was kind of looking at this and I thought, D to me was the weird one. And maybe you felt like one of the other ones was weird, but I didn't like D because I could see that graph A, graph B, and graph C, every X value had one Y value, unlike graph D, where that X value has like all the Y values. Maybe you chose a different graph and maybe you chose a different reason. That's okay. That's up to you. Like I said, no right or wrong here, just curious what you picked out. So let's talk about these relations. And we're going to use this word a lot. So a relation is the mapping between a set of input values called the domain, right? We said the input is the domain, our X coordinates are the domain. So a mapping between a set of input values called the domain and a set of output values called the range. So domain is our input, our X coordinates, however you want to think of it. Range is our output. Range is our Y. It's our dependent quantity, right? Because it depends on the X. So there are lots of different ways to represent these relations. How you get from X to Y. How you get from your input to your output. How you get from your domain to your range. There's a lot of different ways of showing this. One of the ways of showing this is with ordered pairs, like we saw in the warm-up at the very, very beginning. You could show a relationship with ordered pairs, right? How do you get from -2 to 2? How do you get from 0 to 2? How do you get from 3 to -4, right? That's a relation. We also, on the warm-up, showed a relation using an equation, right? An equation shows a relation. If you plug in a number for X and you work this out, what do you get for Y? So this also describes our relation. You're used to thinking of it as slope and a y-intercept. You're not wrong. It's just, this is a different way of showing our relationship. There's other ways. Verbal, you could just describe it. The relation between students in your school and each student's birthday. Is there a relation there? You could write that. You could say it out loud. Sure, that works. We also use something called mapping. You may have seen this before, where we're like, okay, here's all the numbers in my domain. Here's all the numbers in my range. If I plug in a 1, I get 2. If I plug in a 4, I get 5 and -5. If I plug in a 2, I get 0. So this is another way of doing it. And more ways that you're very familiar with, I suspect. You can represent a relation with a graph. Obviously, we can put the points and we can connect them up and be like, there's my relation. We can point out a relation with a table, right? Oh, look, here's your domain, here's your range. You're used to doing X and Y, but it's the same thing. Again, how are we getting from X to Y? How do we get from X to Y? How do we get from our domain to our range, from our domain to our range, from our domain to our range? From our input to our output. How'd you get there? So there are at least 6 different ways to represent this. Now, let's be a little more specific because I used the word function earlier. I used the word function in your last lesson as well, in a previous lesson. So let's get this down, function. A function is a specific kind of relation. A function is a relation that assigns to each element of the domain exactly one element of the range. And again, functions can be represented in all the ways we just showed, with mapping, with a graph, verbally, an equation. You can use all the ways. But the deal with a function is that relation, every input gets exactly one output. Every element in your domain only gets one element in the range, okay? Every X only gets one Y. That is what makes it a function. So we have a few things here. For example, I have a lovely table here. I would like you to take a look at this table and I would like you to decide if it is a function and make sure you tell me why. Remember, function, every input gets one output. Every domain gets one piece of the range. Go ahead and hit pause, jot down your thoughts, and hit play when you're ready to check your work. So this actually is a function, and I'll show you why. My domain, if I plug in a -1, I only get one answer, 1. If I plug in a 2, I only get one answer, 0. If I plug in a 5, I only get one answer, -5. If I plug in a 6, I only get one answer, -5. And if I plug in a 7, I only get one answer, a -8. Now notice 2 of my inputs gave me the same output. That's okay. That's okay. So long as when I plug in a number, I only get one answer out, we're okay. So this is a function. Each element in the domain has exactly one element in the range. Every one of these guys only goes to one of these guys. And they had to share. That's okay. Sharing is caring. It's fine. It works. So I have more of these. I would like you to analyze this relation represented as a mapping. Is this relation a function? And tell me why. Go ahead and hit pause, jot down your thoughts, hit play to keep going. So I'm looking at this one. If I plug in a 1, I get a 2. Ooh, but if I plug in a 4, I get a 5 or a -5. That 4 got a little greedy and tried to give me more than one answer. This is no longer a function. Nope. An element in the domain maps to more than one element in my range. One of my inputs got greedy and took 2 outputs. Not a function anymore. Boo. So now I have a verbal one. Analyze this relation. Analyze the relation represented verbally. Is this relation a function? Explain your reasoning. Hit pause, jot down your thoughts, hit play to keep going. So for this one, it says the relation between students in your school and each student's birthday. Well, I'm pretty sure everybody only gets one birthday. If students are the input and birthdays are the output, you might have to share a birthday, but everybody only gets one birthday. So yeah, this is a function. It's definitely a function. Every student only gets one birthday. You don't get 2, although some of us try, and some of us maybe celebrate birthday month. It's a thing. So you can write an equation representing a function using a special notation called function notation. So let's look at a relationship between an equation and function notation, and you're going to find it's not so bad. So consider this scenario. US Shirts charges $8 per shirt plus a one-time charge to $15 to set up a t-shirt design. So if I'm thinking independent and dependent, I feel like my shirts are pretty independent, right? Looking at my units here. And the dollars, I got dollars. My dollars are going to be my dependent quantity, right? Because the truth is, how much we're going to be charging for these shirts that we're making kind of depends on how many shirts we're buying, right? We want to make a special design. How much we're going to pay for that kind of depends on how many t-shirts we're getting, or shirts. Maybe they're not t-shirts. Maybe they have collars. I don't know. So I could write an equation. Remember that independent is X, dependent is Y. So fine, $8 per shirt plus another $15 to set it up. And that is going to tell me how much money I'm going to be charged for that, how much it's going to cost. So the equation y equals 8x plus 15 can be written to model this situation, right? $8 per t-shirt plus $15 to set it up. The independent variable x represents the number of shirts ordered, and the dependent variable y represents the total cost of the order in dollars. Now, we said that we can take this normal everyday equation. It's nothing special. You've seen this before. We can take this normal everyday equation and rewrite it using function notation. It's actually really easy to do. Function notation is a way of representing our functions algebraically. The function notation f of x is read as f of x. You did just hear me say it. So, and indicates that x is the independent variable. So this is important. This is not f times x. This is f of x. This means that f depends on x. All right, that's all this function notation means. It actually has the independent and the dependent variables like right within it, all in the same notation. So when I say f of x, that just means x is my independent variable and that f depends on x. So this is a function because the number, each number of shirts ordered, the independent value, there's exactly one total cost or dependent value associated with it. So yeah, our t-shirts are our function, right? I plug in, this is how many t-shirts I'm getting. I get one output. That's how much you gotta pay for it. So because this relationship is a function, you can write y equals 8x plus 15 in function notation, and it looks like this. So notice instead of a y, we replaced it with f of x. We replaced it with our function notation. We have, instead of a y, we have the name of our function, which for now we'll just call, f for function. Okay? And of course, our independent variable, which is in our equation, also ends up being tucked inside to show us f is dependent on x. So f of x. If f is a function and x is an element in its domain, then f of x just denotes the output of f corresponding to the input. So all this means is what we keep saying, f depends on x, our independent variable. So the cost defined by f is a function of x defined as the number of shirts ordered. Now, we've used f, we've been using x this whole time, and we've used an f. But the truth is, you can write function notation all kinds of ways. You can use different variables, right? Maybe you don't like f and x, although we use them a lot. But you could write a function in a number of different ways. You could write the t-shirt cost function as c of s equals 8s plus 15. Where the cost, defined as c, is a function of s, the number of shirts ordered. So if you don't like f of x and you're like, so weird, I'm talking about the cost of t-shirts, fine. Your cost can be c and number of t-shirts you order can be s. I don't usually like using s as a variable. It looks too much like f5, but you get the idea. You could change it up if you wanted to help it make more sense. So considering our function, if we were to graph this, if we were to be like y equals 8x plus 15, I'd like to know a few things. I'd like to know what expression in the function equation represents the domain. We removed our x's and our y's, right? We removed our x's and our y's. So what now in this function that we have, c of s equals 8s plus 15, what now represents our domain? And for the next question, what now represents our range? Go ahead and hit pause, jot down your thoughts, and hit play to keep going. So we've said in the past that domain was x, range was y. So this just means, because I swapped things out, that means s now represents my domain. And that means that c, or c of s, represents my range. Now they went all out. They were like, you could say c, you could say c of s, you could say 8s plus 15, just like the whole thing, because c of s does equal 8s plus 15. But if you had just told me that c represents the range of the function, I would have been okay with that too. So what is the possible domain and range for this situation? Remembering that your domain is your t-shirts, your range is how much it's going to cost you. So can you describe for me what numbers you could have as your domain? What numbers could you have as your range? Go ahead and hit pause and jot down your thoughts and hit play to keep going. So let's start with the domain. The domain was t-shirts, right? The number of t-shirts. You either buy a t-shirt or you don't buy a shirt, right? Like you don't buy part of a shirt. That's weird. Maybe some people do. I don't. So I'm going to say the domain is the set of whole numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up forever and ever and ever. That's my domain because that's the number of t-shirts I would buy. The range is a little different, and this is going to sound wordy, but just go with me. The range is the corresponding set of whole numbers that result from substituting values into the expression 8s plus 15. So your range, your cost, remember ranges are cost, your range is also going to be whole numbers, but it's not all of them, is it? It depends on what you plug in for your number of t-shirts. Yeah. Now, one of the easiest ways to tell whether or not a function is a function, whether or not a relation is a function, I'll say this properly. The easiest way to tell whether or not a relation is a function is by using something we call the vertical line test. And maybe it's easiest for me because it's visual, all right? The vertical line test is a visual method used to determine whether a relation represented as a graph is a function. So you do have to have a graph to use your vertical line test. To apply the vertical line test, consider all of the vertical lines that could be drawn on the graph of a relation. Anywhere you would draw a vertical line. If any of the vertical lines intersect that graph of the relation at more than one point, then the relation is not a function. We said to be a function, you only get one output, so it needs to. So any vertical line you draw should only intersect your graph once. If it intersects more than once, it's out, not happening. So you can see for this parabola, which is facing upward, anywhere I draw a vertical line, it's only going to intersect the graph once. So it's a function. But for this parabola that's sideways, that's opening off to the right like that, that's not a function because there are places, lots of places, where if I draw a vertical line, it intersects in two places, not one. Well, darn it. And I also do want to point something out. The vertical line test applies for both discrete and continuous graphs. It does apply to both of them. And if you don't know what I mean by discrete and continuous, I do have some definitions here real quick. A discrete graph is a graph of isolated points. Remember how the other day you guys said that one of the groupings was dotty, right? They just had a bunch of dots, a bunch of points, and it wasn't connected. Remember you guys were like, it's a bunch of unconnected points. That would be a discrete graph. So a discrete graph has points that aren't connected. They're isolated points. A continuous graph is a graph of points that are connected by a line or smooth curve on the graph. So continuous graphs have no breaks. So it can, like, these graphs are continuous. These are nice continuous graphs. Those curves, those lines, they are all connected, baby. There's no holes or breaks in that one. So we would say that these are continuous. So that's the difference between discrete and continuous. Discrete has unconnected points. Not that you can't see a pattern, it just has unconnected points. And a continuous graph, all the points are connected by a line or a nice smooth curve, no breaks. So, how can you determine if a relation represented as a set of ordered pairs is a function? How would you know that? Go ahead and hit pause, jot down your thoughts, hit play to keep going. So a set of ordered pairs represents a function when each x value in the set maps to exactly one y value. And I know we keep saying this over and over again. Every x gets one y, right? We keep saying that. But that's how you can tell in an ordered pair. Make sure that each x value only gives you one y value. If you're like 2 gives you 5, but then 2 also gives you 7, it's not a function. Got greedy. So how can you tell if a relation represented as an equation is a function? Hit pause, jot down your thoughts, hit play to keep going. So how do you know if an equation is a function? Well, an equation represents a function when you can solve for y and you get, I can say this, when you solve for y and get only one y value for any given x value. I think the general rule to follow for this one, and it's not always, but most of the time it'll work for you guys, is if you can get it to look like y equals something. If you can get it to look like y equals something, there's a pretty good chance that you're dealing with a function. That will not always be the case, although I think for us it's mostly going to be because we're only in integrated math 1 after all. Higher levels, you have to worry about that a little more. But again, the big idea is I should be able to plug in x and only get one answer for y. That's the idea. So I've got a few things here. In fact, I got a whole bunch of these. I just have A on my screen, but I got a bunch of these that you're going to do on page M1-45. Determine which relations represent functions. So first of all, decide it's a function, it's not a function. First thing you need to decide. And if the relation is not a function, state why not. If you're like, that's not a function, you better give me a reason why it's not a function. Go ahead and hit pause to work these out. You got a whole bunch on the page, and then hit play to keep going. So y equals 3 to the x power. Well, anything I plug in for x, I'm only going to get one answer for y, right? If I plug in 3 to the 1 power, that's 3. If I plug in a 2, 3 to the 2 second power is 9, right? So any x I plug in, I'm only going to get one answer for y. So it's a function. This relation is a function. B, for every house, there is one and only one street address. I know, Carmel, you all got some interesting addresses. They actually are talking about changing that up a bit. We'll see. But generally, I would say this is true. The relation is a function, right? For every house, there's one and only one street address. If you had more than one address for the same house, it might be a little confusing. Even me in my apartment, while part of my address matches the other people in the apartment, the truth is I have a specific apartment number. That's my address. That's just me. So I only get one address. That's how it goes. What about this one? So I like to kind of be like, all right, if I plug in a -1, I get 4. If I plug in a 0, I get, wait. If I plug in a 0, I could get 0. Or if I plug in a 0, I could get 4. What? I could get 2 different answers if I input a 0? This is not a function. The domain value of 0 has more than one range value. You got a little greedy. It's rough. What about this one? What about D? Well, right away I see a problem. Like 4, if you input a 4, you get a 9. Input 6, you get a 9. Input 8, you get a 2. But check this guy out. If you input a 2, you could get a 7 or a 20. What? So I have an input value of 2 that gives me more than one output value. This is not a function. Not cool, man. Not cool. Ooh, here we go. Is this a function? Well, let's see. If I plug in a -7, I get 5. If I plug in a -5, I get 5. If I plug in a 2, I get -2. If I plug in a 3, I get 5. So there are some shared output values, but you know what? If I plug in a -7, I only get one answer. If I plug in a 2, I only get one answer. This is a function. That's a function. Yeah. Oh. It's a graph. Did you use the vertical line test? Oh, yeah. Did you use the vertical line test? Anywhere I draw a vertical line, it should only touch once, which it does. It's a relation. This relation is a function. Rock on. We're awesome. Can we come back for a moment to something we were discussing in the last lesson? Remember Judy's group with her graphs D, K, and O? You remember this? Can you take a moment to analyze the 3 graphs Judy grouped together from that last lesson, graphs D, K, and O? Are the graphs she grouped functions? And explain how you know. Go ahead and hit pause, jot down your thoughts, hit play when you're ready to check your work. So because I see graphs, my thought is it's time to use some vertical line tests. And so I drew a vertical line and boom, dude, this guy already failed. It hits twice, once, twice. I use the vertical line test here and oh my gosh, failure epic. It hits twice. Boo, it's supposed to only hit once. And for this guy, well, it doesn't hit at all if I come over here, but it hits forever over here, doesn't it? Ugh. Fail, fail, fail. These are not functions. None of these are functions. None of them. These graphs do not pass the vertical line test. They're not functions. So here's what I'd like you to do. Remember how I told you to save those graphs from last time? We're pulling them out now. I would like you to pull out all these graphs. All the graphs from last time. You had like 19 of them. Can you pull out all the graphs from last time? And I would like you to use the vertical line test to sort the graphs in the previous lesson into two groups. So I want you to take all the graphs from the other day, and I'm going to sort them into two groups, functions and non-functions. And then I want you to record your results by writing the letter of each graph in the appropriate column in the table that's below here on page M1-46. So sort them into functions and non-functions and just write the letters of your functions in there. Go ahead and hit pause to go through and work this out. Go crazy with that vertical line test, and then hit play when you're ready to check your work. So I don't think I quite have all my graphs up here. I think I'm missing a few. I think I'm missing R and S, but I have my other graphs up here. I'm just going to go vertical line test crazy. Is that all right? We're just going to go nuts with this. I'm like, boom, he passes. Boom, he passes. He passes. He passes. That one passes. That one passes. Sorry, my vertical lines are terrible. This guy passes. Oh, that one does not pass. Boo. You know, this has a bunch of dots, but still, it only hits once. This guy passes. This one does not pass. Boo. That one passes. You know, this one has very few dots, but anywhere that I draw a vertical line, it'll only hit at most once. It passes. This guy passes. Oh, another fail. You don't pass. Again, this guy's dots, but still, we can use the vertical line test. It should only intersect once, which it does. That's good. And one more. Oh, yeah, he easily passes. Sorry, I don't have R and S up here. I don't know what happened to my R and S graphs. Sorry, my bad. But hopefully you figured out that R and S were both also functions. They also both passed the vertical line test. Sorry, I didn't have them up here. So A, B, C, E, F, G, H, I, J, L, M, N, P, Q, R, S. And yes, it sounds like I don't know my alphabet very well, but all of those guys are functions. And then D, K, and O, we've already established, not functions. So as always, guys, I know this was a long one, but I hope you found it helpful and I hope you found it useful. Let me know if you got questions, email me, come see me during office hours, come talk to me, and I'll see you soon. Bye.